Next, we come to another feedback solution, which is the derivative frequency error detector. Let us recall that the correlation always leads us to removing the effect of the modulated symbols. We have discussed this before in the context of carrier phase synchronization and in the discussion on phase-based frequency error detector. Now, the problem here is that we do not know AM. Those were data edit scenarios where the data values were available in the form of a training sequence or the decisions we make on the match filter outputs. Now, when the data symbols are not available, we need to resort to a non-data edit solution. What we do is that we replace AM with the match filter output, and this leads to the correlation output as the energy mod ZNTS square. One difference you will notice is that here the indices are MTM and here we have NTS. This is because we are not down converting to one sample per symbol anymore, and instead we are taking L samples per symbol and the counter is running on sample times. There is an intuitive reasoning why this maximization of the energy perspective works. Assume that this is the match filter and this is the incoming signal. So you see, when the difference between the center frequencies is large, which means that the CFO is large, then the overlap is small and we have a relatively low level of energy. As the CFO reduces, the overlap increases and the energy increases. For a full overlap between the incoming signal and the match filter, we have the maximum energy available. This implies that in a feedback solution, we focus on the energy at that time instant, not on the summation part. We just use this as an expression. Now, to find the maximum of this energy curve, we equate the derivative to 0. The purpose of an FLL is also to drive an error signal to 0. So what we do is that we form an error signal by taking the derivative of this expression. If we ignore complex operations and just assume real operations, then we can see that the derivative of this expression is 2z into z dot, where z dot is the derivative. In terms of complex expressions, we have an in phase term and we have a conjugate in here. The derivation is in my book, but I hope that this makes sense if we just assume real signals. Now there are two possible routes for this implementation. One is that we have the match filter output and we employ a derivative filter that takes a derivative of this output in real time. And then we multiply these two signals. In a delay sensitive application like an FLL, the delay of this filter can be significant. So we instead employ a frequency match filter in which we have a match filter and we take pre-computed derivative of this match filter, which is called HFMF, frequency match filter. Both are driven by the same input and both produce the output at the same time, which can be multiplied and used as an error signal. At this stage, remember that this dot operation, the derivative, is in frequency domain. So let us see what happens when we apply this operation. The incoming signal is filtered by a square root raised cosine pulse, and when we take the derivative of this pulse, this constant bandwidth has a derivative of 0 and transition bandwidth is cosine, so the derivative is a sine. This frequency match filter is also called a band edge filter, although we will see other band edge filters in the coming slides. One point to notice here is that only the transition bandwidth contribute towards forming the final filter. This is why you often read this statement from Fred Harris, which says that the excess bandwidth provides the energy for synchronization purpose. Later we will see that this same setup can also be used for timing synchronization. One drawback of a frequency match filter is that it is discontinuous at the edges, here and here. The shape is not smooth. Therefore, in time domain, impulse response is very long. Any signal that is narrow in frequency domain is long in time domain. One solution is that after taking a derivative of this transition bandwidth, we continue the spectral shape of this sine in the same trajectory here and here. That makes the shape smooth and the impulse response can be constrained. We can say that the final spectral transition forms a half cycle of a sine wave. This was a quarter cycle and this was another quarter cycle, half cycle. In the error signal, we are multiplying these two terms in time domain. What will happen in frequency domain? A convolution. This is the shape when there is no CFO present, and this is the shape when there is a carrier frequency offset present, where you can see that at the DC we have a spectral shape that resembles an impulse. The magnitude of this impulse indicates the extent of the frequency error. One problem here is that the convolution of two terms like these involves the whole bandwidth of this match filter output. So imagine this shape rolling over this spectrum. Even in this region, when we don't need any output, even then there will be an overlap, and we have signal at these frequencies which, due to this convolution, which could be avoided. Since these terms arise from the interaction among the symbols themselves, we call it self noise, modulation noise, or pattern noise. Ideally, we want, when there is no CFO present, we have a signal like this, even lower, and in here we want something like this. So let us break the modified frequency match filter into two terms. One is the lower band edge filter and upper band edge filter. So we call it the lower band edge filter and the upper band edge filter. By adding these two, we get an even band edge filter because its response is even symmetric around the zero frequency. And if we subtract this one from this one, we get an odd band edge filter because this kind of shape is called an odd signal. We discussed this in lecture number 1. Why are we doing this? Now, we see that when we replace the match filter output with the output of the even band edge filter and keep the odd band edge filter as it is, we can form a new error signal which is given by the product of the two quantities. When the convolution happens in frequency domain, you can see in the case of no CFO there is hardly any signal present, and in the case of a frequency offset, all the extra spectral components are gone. In this slide we are deriving the impulse response of the band edge filter. If you want, you can ignore this slide and move forward. First we form the impulse response of this spectral shape, because after having the impulse response of this shape, we can translate it to here and we can translate it to here. This will be the even band edge filter, and when we invert this one we will get the odd band edge filter. You can see that this is a cosine shape, and the period of this cosine shape is given by 4 alpha over Tm. This is because this bandwidth was alpha over Tm, and then which was a quarter cycle, so the complete period becomes 4 alpha over Tm. A cosine in frequency domain has two impulses in time domain. We have an impulse at Tm over 4 alpha minus Tm over 4 alpha. Next, we multiply this cosine with the rectangular signal like this. Only then we get a spectral lobe like that. This rectangular signal has a sync signal in time domain, and the zero crossing of the sync signal are, as we told in lecture number 1, given by the width of this rectangle, which is Tm over 2 alpha, inverse of this width. Next, this multiplication in time domain is convolution in frequency domain, and we get this red shape here and red shape at the position of this impulse here. When we add these two, we get the cumulative signal. This we translate to here, and we get the. Now there is an intuitive reasoning for using the band edge FLL for frequency recovery as well. Recall that the error signal is given by the output of the even band edge filter multiplied by conjugate of the odd band edge filter. While the derivation is in my book, it comes out to be ZBE minus NT square minus ZBE plus NT square, where minus and plus for the lower and upper band edge filters. This was a lower band edge filter and this was the upper band edge filter. If you take the energy out of this and subtract the energy out of this filter, we get a measure of our carrier frequency offset. And this makes sense as well. This is the spectrum of an incoming signal. If it is tilted towards the right, the energy from this filter will be larger and energy from here will be smaller, and vice versa. This expression makes intuitive sense that we have to subtract the energy out of the upper bandage filter from the lower bandage filter. This energy difference perspective reminds me of my childhood days where street hawkers used to roam around in the streets with this handheld weighing scale. They used to put objects on one side and the weights on the other and balance these two, just like we are trying to balance the carrier frequency offset right at the middle of the two bandage filters. This is a block diagram where we can see upper bandage filter, lower bandage filter, and we are subtracting the energy out of them and use it as an error signal to drive the FLL. One question that remains is that if we are using the upper and lower bandage filter, why did we form the even and odd bandage filters? This will be answered in the lecture on timing synchronization.
I have made this flow graph to demonstrate the working of a bandage frequency error detector. The excess bandwidth is chosen as 0.5, samples per symbol is 16, the sample rate is 32,000, and the carrier frequency is 6,000. Frequency offset is chosen as a slider from minus 3000 to 3000 Hz. Now, this is the coefficients of a negative band edge filter, which have been computed offline, and these are the coefficients of the positive band edge filter computed offline with the help of the procedure described in the text. These values were chosen for an excess bandwidth of 0.5 and samples per symbol as 16. After the base generation, we have a custom QAM block where the frequency offset is introduced here, and the rest of the parameters take values from these variables. Down converter is implemented through a local oscillator INQ arms and an INQ mixer. This is therefore the down converted spectrum. While this looks a little complicated, I have a noise source whose spectral density is flat. When given as an input to the negative band edge filter and the positive band edge filter, it just draws for us the spectral responses of the positive and negative band edge filter along with the down converted spectrum. This will help us visualize as we shortly see. This frequency distorted QAM waveform is given as an input to the positive and negative band edge filter. The energy is computed and the energy from the positive band edge filter is subtracted from the energy from the negative band edge filter and plotted on a time sync. Let us run the flow graph and see how it works. The received spectrum, since it's a real waveform, we have a symmetric spectrum around frequency 0. Since we already know about this, I take this out of the focus. And now we see the down converted spectrum in the case of a 0 carrier frequency offset gives us this waveform where this part is down converted to 6 minus 6 0 and minus 6 minus 6 minus 12 kilohertz. The two spectra of the negative and positive band edge filters are plotted here so that when this spectrum slides, we can see the effect as well. The frequency error detector output is 0. Let us introduce a carrier frequency offset of 100 Hz. This spectrum has slightly shifted to the right. And if you can see, the overlap with the positive arm is more than the overlap with the negative arm. This is more clear if we introduce a 200 Hz offset. And now you can clearly see that the overlap with the positive arm is more than the overlap with the negative arm. Energy is computed after filtering, therefore the product, this product is a smaller value, this product is a larger value. And the fed output, the frequency error detector output, is the negative band edge filter output energy minus positive band edge filter output energy, and hence it is a negative value in this case on average. Rest, if we keep sliding the spectrum, we will see that the overlap with the positive arm gets bigger and bigger, the overlap with the negative arm gets smaller and smaller. Similarly, this happens on the other side as well. For a negative carrier frequency offset, you can see that the output from the negative arm is much bigger as compared to the output from the positive arm. Just observe the overlapped spectra in positive band edge filter and the negative band edge filter. And therefore, this minus this is a positive term, which we can see here on average, this will generate a positive output, which will drive the loop towards zero carrier frequency offset. And if we keep doing this operation, we will see that the overlap with the positive arm is almost vanished. And the only output is from the negative band edge filter.
Let us take a GNU Radio example where there is an FLL band edge block. The inputs of this block are samples per symbol, which is given by our parameter L, which we have extensively discussed in these lectures. The filter roll-off factor is given by alpha, excess bandwidth of our root raised cosine pulse shape. The prototype filter size is the number of coefficients, and the loop bandwidth we have already discussed during the lecture on carrier phase synchronization. As an example, for a 16 QAM modulated signal and a CFO of minus zero point 0.2, which is normalized with respect to the symbol rate, loop bandwidth of 2 pi over 250, excess bandwidth of 0.5, and L is equal to 4 samples per symbol. Here you can see that the input signal is suffering from a heavy CFO. However, the output signal has a CFO-free shape, while there is a timing error and there is a phase error still present, but the CFO has been removed. You can see this in the phase diagram, and this value of 1.25 of the frequency comes from 2 pi into 0.2.
Having understood the intuition behind the working of a band edge frequency error detector, we see the working of an FLL band edge block that comes with the GNU Radio companion. Sample rate is defined as 32,000. There are 4 samples per symbol. The excess bandwidth is 0.5, and the frequency offset and the loop bandwidth are defined through the sliders. There is a tab widget which is used to observe the time domain waveform and the spectra. After zeros and ones generation, the input is given to a custom QAM waveform block, which we have discussed in lecture 3. The excess bandwidth, samples per symbol, and the sample data is taken from their respective values. A frequency offset is introduced through a complex sinusoid block whose frequency is frequency offset defined by the slider. The input is given to the FLL band edge block. Other than this, there are the received signal and the received spectrum are observed here, as well as the FLL output and the recovered spectrum from this output. These three signals, frequency, the estimated frequency, the phase, and the error signal, are observed through the time sink. Now, the FLL band edge consists of a relatively few number of variables, which are the samples per symbol, excess bandwidth, and the loop bandwidth. The prototype filter size defines the number of coefficients we want for the band edge filter. Let us run the flow graph to observe its output. For a zero frequency offset, we can see that the received signal is a quite smooth QAM waveform, and the FLL output is also similar. Remember that this is not raised cosine pulse shaped output, this is a root raised cosine pulse shape, because the operation of a band edge frequency error detector is occurring at a rate of samp per sim samples per symbol. In this case, 4 samples per symbol. That basically is before the match filtering is implemented. Let us introduce a frequency offset now. And we can see that the received signal is distorted by a frequency offset, and the FLL has not been able to recover it. Neither the error signal is stable, and nor the FLL output is as clean ones and zeros approximately. This is because the loop bandwidth is default value is 0. Let us increase the loop bandwidth, and from an observation of these two waveforms, it seems that the FLL has converged. This is also clear from the error signal, where we can see that the phase has become quite smooth, which means that this is tracking a frequency error, and the frequency has comes out close to minus zero point 0.2. This is because the frequency error is 1000 and the sample rate is 32,000. 1 over 32 multiplied by 2 pi. Let us observe the spectrum as well. So we can see that the received spectrum is shifted by 1 kilohertz in this case, and the recovered spectrum is centered around 0 kilohertz. And then we can increase the frequency offset and see the spectrum sliding towards the right while the stable output from the recovered spectrum. We can also observe this through the negative frequencies, and the minus 2 kilohertz is the frequency output, and this slope of this phase slope has become positive. FLL should now increase its frequency because the input carrier frequency offset is negative. For a negative 5 kilohertz. Keep in mind that FLL band edge is one of those few blocks in GNU Radio whose documentation is actually very clear. So here we can see that the frequency lock loop derives a band edge filter that covers the upper and lower bandwidths of a digitally modulated signal. In practice, the above equation can be simplified by just comparing the absolute value squared of the output of both filters. Absolute x lower xl square minus absolute x u square, lower and upper. This is exactly what we discussed in the intuitive viewpoint of the band edge filters. The rest of the details are discussed in both in the text and in the lecture, where we have formed an even band edge filter, which is CCT, and an odd band edge filter, which is SST. The even band edge filter is summing the upper and lower band edge filters, and the odd band edge filter is subtracting the lower band edge filter from the upper band edge filter. This, I think, is different than what we have covered. The error signal is formed as the product of the even bandage filter output times the conjugate of odd bandage filter output. The real part drives the frequency lock loop, and later in the discussion of timing synchronization, we will see that the imaginary part or the quadrature component of this error signal drives the timing lock loop. We have discussed in the past that feedback loops cannot be implemented in GNU Radio Companion. However, they can be implemented in GNU Radio itself. So we go to the FLL band edge code of the GNU Radio and see how it works. Then we will be able to change the code itself or form our own custom blocks. As discussed in detail in both the lectures and the text, the impulse response of the band edge filters is formed by summing two sync signals and then modulated the resultant signal to the respective point. After that, we come down to see how the actual error signal is implemented, and we see that this is the output of the upper bandage filter, the output of the lower bandage filter, and the error is formed by taking the norm of the lower minus upper bandage filter. And norm just is the L2 norm, so it is the magnitude squared of the lower bandage filter output minus magnitude squared of the upper bandage filter output, which corresponds to the energy in those filters. This is what we discuss in the intuitive viewpoint of the band edge frequency error detector.
The role of the functions advanced loop, phase rep, and frequency limit has been discussed before in a lecture of Module 4. In summary, for a small CFO, the timing is recovered first, and the matched filter output is downsampled to one sample per symbol. Next, the modulation is removed through the product with the data symbol conjugate and the underlying waveform. Just like in the case of carrier phase offset was a constant complex number, here it is a complex sinusoid, the frequency of which is the carrier frequency offset we desire. For a large CFO, energy maximization perspective comes into play, which can be achieved through a derivative frequency error detector or a band edge FLL, or many other techniques are also possible.